Heidi-ho, Renaissanceteers! Stephen J. here with the solution to puzzle number 253, a challenge to our Renaissance mathematicians. I will cover a bit of calculus in this presentation, but I have tried to make it understandable to everyone without prior knowledge of calculus. The important thing is to understand how the math is applied to find the solution.
My cousin Kurt noticed this problem on a bulletin board in Boston University. He snapped a photo of it and sent it to me as a challenge. It has a surprising solution. Here is the puzzle. Take the number 25 and break it up into any pieces you want. For example, 10 plus 10 plus 5, or 24 plus 1, or 3 plus 2 plus 15 plus 5. These are all combinations that sum up to 25. What is the greatest product you can make if you multiply those pieces together? Will your strategy work for any number you choose? If you would like to solve the problem for yourself, now would be the time to pause this video. Otherwise, just stay tuned and the solution presentation will begin. And so we begin. If we allow fractional numbers, there are an infinite number of ways to break the number n into pieces. Let's see if we can narrow down the options for finding a set of pieces that multiply to yield the maximum product. Consider the case of dividing the number into two equal parts of size z. Their product is z times z, which equals z squared. Now for comparison, divide n into two unequal parts, z plus b and z minus b, so that they still sum up to the number n. When we multiply them, we get z plus b times z minus b is equal to this chain of terms, which is equal to z squared minus b squared. Z squared minus b squared will always be less than z squared. Therefore, to obtain the maximum product for two pieces, we need to make them equal. If you break n into more than two pieces, you will find that the product of those pieces is maximum when they are equal as well. And for a bonus Renaissance point, prove this claim. So knowing that we want to break the number 25 into equal pieces, we still need to determine how many pieces of what size will produce the maximum product. We could think about it really hard, or we could be lazy and use the LACFI method. LACFI stands for let a computer find it. If we take the number 25 and break it up into n pieces, each piece will be of size 25 divided by n. And since we want the product of all n pieces, we must calculate 25 divided by n to the n power. Let's make an Excel table and see what it looks like. So here we have a table of three columns. In the first column, we have the value n, which goes from 1 to 25. In the second column, we have 25 divided by n, goes from 25 down to 1. And in the third column, we have 25 divided by n to the n power. We see that the maximum product occurs when we divide 25 into 9 pieces of size 2.78. 2.78 is close to a number of eminent importance in mathematics called e. E is an irrational number like pi, and e approximately equals 2.7182, 818, 284, 59, and on to infinity with no repeating decimals. We will learn more about e later in this presentation, but right now let's create a different table where we vary the piece size rather than the count. So now we have a table with two columns labeled x and x to the power of 25 divided by x, and we have a plot of the data. X represents the size of the pieces that we are chopping the number 25 into, and therefore 25 over x is the number of pieces. So x to the power of 25 divided by x is the product of all the pieces. And again, we see that the maximum occurs when the piece size is near 2.7. We have plotted the curve as a series of points with the value of x incrementing in steps of 0.1. If we wanted to get a more precise estimate of the maximum value of x to the power of 25 over x, we could use smaller increments. But there is a better and mathematically precise method. Imagine the curve as a hill, and you are walking from left to right up the hill. In this region, the slope is positive. After you pass over the crest of the hill, you begin going downhill, and the slope is negative. But at the very tippity top of the hill, the slope is 0. So if we could compute the slope of the curve at every point, and find where the slope passed through 0 in going from positive to negative, we would have the exact maximum value of x to the power of 25 over x. Finding the slope of a function is the object of differential calculus, and the process is called differentiation. The slope of a function is called its derivative. We will see how to find the derivative of the curve using calculus, but first, for illustration, let's find the approximate slope, letting the computer do the work for us again. For example, let's find the slope at the point where x equals 2.1. A line segment drawn from the point before to the point after gives the approximate slope. We have the x and y values for the points on each side, and so it is a simple matter to compute the slope as the change in height divided by the horizontal distance traveled. So let's repeat this process to compute the slope for all the points in our curve and add a slope column to our table. And let's add the plot of the slope to our graph. Now look at where the slope crosses 0. It is not exactly at one of the plotted points. Let's zoom in on it. In our table, we have the values of the points before and after the 0 crossing. So we can do a linear interpolation to find the more exact 0 crossing point of 2.71973. This is even closer to that special number e. But so far, we have let the computer do all the calculations for us. Let's get down to business and do some real math. Now we are going to differentiate the function y is equal to x to the power 25 over x to find its exact slope. So once again, here is our function y is equal to x to the power of 25 over x. Also written like this. We want to find the slope of the function y, which is delta y over delta x, as delta x gets infinitesimally small. This is the definition of a derivative in calculus. It is normally written in this notation. Mathematicians have compiled tables of derivatives for many functions. But there are so many functions that no table could cover them all, and you are not likely to find the derivative of x to the power of 25 over x in them. So we must use our math skills with the help of the tables to work out the derivative of x to the 25 over x power. If you don't know how to solve a particular problem in mathematics, sometimes you can transform it into a problem that you do know how to solve. We will do so by making use of the inverse functions e to the x and the natural log of x. Inverse functions do the opposite of each other. For example, the square of x is the inverse of the square root of x. So, square root of x squared is equal to x. Likewise, e to the log natural of x is equal to x. So we can rewrite x to the power of 25 over x as e to the power of log natural of x to the power 25 over x. This is helpful because log natural of x to the 25 over x simplifies to 25 over x times log natural of x. So we've gotten rid of that exponent. So our function becomes e to the power of 25 over x times log natural of x. This new expression is a function of a function, as in f of g of x, where f of g is equal to e to the g power, and g of x is equal to 25 over x times log natural of x. The derivative tables say use the chain rule in this case. So the derivative with respect to x of f of g of x is equal to the derivative with respect to g of f of g times the derivative with respect to x of g of x. So this is equal to our function above, the derivative with respect to g of e to the g times the derivative with respect to x of 25 over x times log natural of x. Let's take a look at the derivative of e to the g. Here is a table of values for x and e to the x power. And here is a plot of the data. As x gets larger, the curve rises faster. E to the x is also called the exponential function, and its rapidly increasing slope is called exponential growth. If we plot e to the negative x, the curve is reversed and we have exponential decay that asymptotically approaches zero. There are many examples of exponential growth or decay in nature. It occurs whenever you have a quantity whose rate of growth is proportional to how big it is. For example, population growth is exponential until it runs into limiting factors, like lack of resources to support it. The falling temperature of a cup of coffee resting on a table is an example of exponential decay. Now I'd like to show you something remarkable about e to the x. Let's go back to our table and graph of e to the x and compute the slope of the curve at each point, as we did once before by taking delta y over delta x. And now let's plot this slope data on the same graph. Lo and behold, the slope of e to the x is exactly the same curve as e to the x itself. So the derivative of e to the x is equal to e to the x. We will make use of this right now in differentiating our function e to the power 25 over x. Let's recap what we have to this point. If we divide 25 into equal pieces of size x, then the product of all those pieces multiplied together is x to the 25 over x. To find the value of x that yields the maximum for x to the 25 over x, we find where the slope, also known as the derivative of x to the 25 over x, is 0. We have shown that the derivative of x to the 25 over x power is the derivative with respect to g of e to the g times the derivative with respect to x of 25 over x times log x, where g is equal to 25 over x times log x. And now we know that the derivative with respect to g of e to the g is equal to e to the g. And this is equal to e to the 25 over x times log x, which is equal to x to the 25 over x. So now we just need to find the derivative of this term. And for this, we use the product rule. The product rule says that the derivative of a product of two functions, f and g, is the derivative of f alone times g plus f times the derivative of g alone. So applying this rule to our function, we get this. And using the rules found in the derivative tables, we get, and finally this simplifies to, now we can combine this result into our original equation. And we get x to the 25 over x times 25 over x squared times 1 minus the log natural of x. This is the exact equation for the slope of x to the 25 over x. Let's see how it compares with the approximation we plotted earlier. So here we have our function x to the 25 over x and its approximated slope. Now let's add to the table a new column with the values calculated by our derivative of x to the 25 over x. And let's plot this new data. Look at that. Our derivative of x to the 25 over x matches nearly perfectly with the approximated slope curve. Now you may think that I am a nerd, but that makes me smile, because it not only confirms that all these fancy schmancy calculus formulas really work, but it also confirms that we applied them correctly, and that's a big deal. If we zoom in on this area, you can see that it is not a perfect match, but that is to be expected since the orange curve is just an approximation. The green curve is exact. Remember that our first objective was to find the value of x that made x to the 25 divided by x a maximum. And to do that, we set the derivative to 0 and solve for x. So let's divide both sides by x to the 25 over x, and that cancels out. Likewise, we divide both sides by 25 over x squared, and that cancels out. So notice that the number of 25 is now gone completely. Ladies and gentlemen, number 25 has left the building. So that means the solution we're finding would be valid for 25 or 50 or 100 or any number you want. So let's continue. And we have now simplified to 1 minus log x equals 0, which simplifies further to log x equals 1. And finally, that simplifies to x is equal to e, which is what we suspected all along, but now we have proven it. So to find our maximum x to the 25 over x, we set x equal to e, and we get approximately 2.718 to the 9.197 power, which equals approximately 9,867.3, which is the answer to our original problem. But recall that the problem statement showed examples of the number 25 being broken up into integers. So what if we require that the number 25 be broken up into integers? Our math study showed that we need to make the value of x be as close as possible to e, and the closest integer to e is 3. 3 goes into 25 8 times with a remainder of 1, so the multipliers would be 3 to the 8th times 1, which is equal to 6,561. But this is not the maximum possible product. Recall that we get a maximum when all the multiplicands are equal. We cannot make them all be both integer and equal, but we can change the last two numbers from 3 times 1 to 2 times 2. That improves the product to 3 to the 7th times 2 squared, which is equal to 8,748. This, I believe, is the largest product you can make, using positive integers that total to 25.
And so, Renaissanceteers, thank you for watching this presentation. We covered a lot of material in just 18 minutes. If you had never studied calculus before, I hope this served as a good introduction for you. And in closing, I would just like to leave you with a bit of cautionary advice.
Alcohol and calculus don't mix. Please, don't drink and derive.